2 with Mr. Clausen. Today we're going to talk about rational functions and asymptotes. So specifically in this video, we're going to look at how to identify some points of discontinuity. This is just when a function either has a vertical asymptote or maybe there's just a gap in the trend line for various regions based on how the function is designed. We'll look at how to identify vertical asymptotes, horizontal asymptotes, and then just do some basic sketching of rational functions and how we can go through some of that just by looking at the equation is really what we're looking for in this given video. So without further ado, let's get started here. So to identify points of discontinuity, the real basic idea that you have to explore here is just, is there a situation where the denominator is equal to 0? And if that's the case, your denominators cannot equal 0. All right, if they equal 0, then you have a undefined function, and then you're going to have a point of discontinuity. So with an example like this, the easiest way to go about this is to simplify it as best as you possibly can using tools like we talked about in chapters 4 and chapters 5. So or unit 4 and unit 5, which was on parabolas, for example. I guess that was chapter 5 in our textbook, and chapter 6 in our textbook looked at polynomials, and we looked at a lot of different tools for factoring things out and whatnot, and that's what we're going to explore using today to help us out. But if we look at this given equation, we can go and we can look for things like common factors. So we see that x's are present in both of these, so I can separate this out and go x, and what we'd have left is x minus 3. And now this denominator would be completely factored. Now, going back to this idea of how we identify a point of discontinuity is we're just looking for, really, restrictions. That's how we labeled it back in chapter 1. This isn't necessarily a new skill. This is just we're applying a different concept to it since we're looking at inverse variations or reciprocal family functions and those type of things. So now what we're just going to do is to identify these points, we're just going to say, hey, does this equal 0? Because if we apply the zero product property, we can look at the situation and just say, hey, if x is equal to 0 and x minus 3 is equal to 0, both of the values for x in this situation are going to be points of discontinuity. So we're going to go add 3 to both sides. X is already equal to 0, so our solution in this case is x is equal to, or x cannot be equal to 0, 3, because these circumstances would cause these points of discontinuity. So that's really the basic idea in a nutshell, how we do this. And so now, to review some of the stuff that we've looked at in the past here, we are going to do some additional factoring here. So for example, we have this. Now we have an a term that does not equal 1, and we have a little bit of grossness going on here. And so just as a quick refresher, typically we would look at a polynomial function as ax squared plus bx plus c, and if we go a times c, that would give us negative 14 in this case. And if you look at the factors of a times c, there's two different things that we can take into consideration here. If we can look at the factors of a times c, and we can have any of them that are added together to equal the b term, then you are all set in figuring out the basics of how to factor this out. So for example, if we go -2 plus 7, we're going to find that this equals the b term, which is equal to 5. And you would just, if you didn't find it on your first try, you would just look at some of the other combinations. This would give you -5, and, let's see, -1, 14 would give you -14, so those aren't possibilities. So you could just go through the factors of a times c and see if any of them equal 5. Now -2 and 7 do. Now since the a term is not equal to 1, what we're going to do, instead of just immediately applying these two terms to separate out the trinomial quadratic here like we did early on in chapter 5, what we're going to do is say 2x squared and now start going negative 2x plus 7x minus 7. And the main idea that you should see here is that negative 2x plus 7x is still 5x. We did not change the fundamental nature of the quadratic here. All we did is we added this extra term. But what this extra term allows us to do is it gives us the factors of a times c. And in the end, what it's going to do is allow us to go and factor this out. And you'll see that I grouped the 2 with the 2 and the 7 with the 7 because those are both prime numbers that go with each other here. And so what we can do now is say 2x. We can go 2x times x minus 1. That's that factored. And then we're going to go plus 7, which is also equal x minus 1. And the goal that you're achieving here, if you do this correctly, is that you'll have the same binomial that can be factored out of both terms. So now we're going to factor x minus 1 from both terms. And now you'll get x plus 7 times x minus 1. And now we can apply the zero product property and just look at circumstances where those are not going to be equal to 0. What we're looking for is we are looking for the values of x that make this not true, or make this true, I should say, because we need it to not equal 0. So let's just solve this like we're trying to figure out if it equals 0 or not. Subtract 7 from both sides and divide by 2. So 2x equals negative 7. Divide all that by 2 and find that x cannot equal negative 7 over 2. All right. Again, I'm just setting it up this way using the zero product property to find the answer I'm looking for, but then this is one of the restrictions that we have. And then the other one is just x minus 1. Let's say x minus 1. Can apply that. Add 1 to both sides. And that's the other restriction. So in this given case is, we're identifying these restrictions, and these are the points of discontinuity that we are facing with in this present situation. And so that's the basic idea that you are trying to apply when you're looking for points of discontinuity. Now, if we move on to how we identify vertical asymptotes, what we're trying to do here is go and still look for these situations where the denominator is potentially equal to 0. Because if the denominator equals 0, that value cannot exist, or it causes the function that we're looking at to be undefined, and so it doesn't work. So we're going to do this again. So the basic idea here is you probably don't even need to do any complex math when we look at this situation. We could probably just set up this basic equation like this and add 3 to both sides and say, hey, x cannot equal 3 theoretically. So this means, okay, using this idea of the zero product property, that at x equals 3 is where a vertical asymptote is present. And if you think about what an asymptote is, it's just this imaginary vertical boundary, all right? So if you have, let's say your coordinate plane here, 1, 2, 3, and then you have, sorry, it's not a very straight coordinate plane. We'll just say it's tilted back a little bit. But this is at x equals 3, and this is just an imaginary boundary that's built into the reciprocal function here and causes the function to abide by that boundary. So the whole shape is going to be dictated by this boundary, and we know the shape from previous lessons as going to be a rightward shift, all right, because you have that h term that's typically there if we're looking at the combined function. So now the same thing applies here, and nothing really changes, because now when we look at this given situation, we're going to split this up fully. So again, let's go 3 times 10. That'll give us 30. And now we're going to look at increments of 30 to see if we can get a sum of 17. Again, I see the 2 and 15. Just work through all the multiples of 30 if you need to figure it out. But, you know, if we add those together, we get 17. So these are the factors that I'm looking at. Now, all this does is it splits this apart. 2 plus 15 is 17. All right? So we're unfoiling it. We're foiling it backwards. And so we'll do leaf, or I don't know how you'd say foil backwards, but that was just kind of a fun attempt. So we're going to go 3x squared. And I know 15 has a factor of 3 in it. So I'm going to go plus 15x plus 2x. And then we'll go plus 10. So again, that original trinomial has not changed. We're just adding that fourth term there, so which could easily be combined. But don't combine it because you're just undoing everything. And now we'll go 3x from both of these terms. And that'll give us x plus 5. And then we'll pull a 2 out of this, and this will also give us x plus 5. Mission success. The two binomials present are the same, so we can factor the two binomials out. So now we can go 3x plus 2 and x plus 5. And in this case, one thing I'm going to do before I get carried away here. So now that we have these factors, typically I would set this equal to 0, but I'm going to do one other thing before we get there. Because just because, you know, if x equals negative 2/3 or negative 5, that doesn't exactly mean there's going to be a vertical asymptote. It might mean there's still a point of discontinuity there, but not necessarily a vertical asymptote. So what I'm going to do here is I need to take the numerator into consideration as well. And so a times c, we get negative 12. And then looking at those factors, let's go negative 3 times 4. So we add those together, we'll get positive 1, so that's how it's going to split apart. And so we'll go 6x squared minus 3x plus 4x minus 2. Now, I did have to take a little bit of a guess at this to figure out the distribution, but I see 2 goes with 4, 3 goes with 6 is going to be an even multiple. So that's just something you kind of have to navigate and see how that's going to work. So we'll pull 3x out of both of these terms here, and we'll get 2x minus 1. And then we'll pull out a 2 here, and then we'll get 2x minus 1 again. Now, the main reason I do this is now if I go and I pull this out down here and I show this out, we're going to have 3x plus 2, and we're going to have 2x minus 1. And if we're going through this, all right, this is the numerator, this is the denominator, and I want to combine both of these now. So if I solve out this whole thing by going and crashing these through and blocking them out as such, we can always go and solve these out. And probably just a general rule of thumb is that if you're asked to simplify anything or identify any asymptotes, just go crash through the whole thing. In the main idea of this course, you're going to want to just simplify all of this out because you're going to want to see if any of these binomials match. And in this case, this binomial matches that binomial. And then once you go and you combine all this together, the new y equals binomial or rational function that you're going to get here is 2x minus 1 all over x plus 5. Now, the reason I bring this up in this situation is that this specific binomial, the situation where x couldn't equal 5 technically, this is going to be where the only vertical asymptote is present. So at x equals 5 will be a vertical asymptote. And if you go and graph this out, this is the only place where you'll see it. You won't see it at negative 2/3 because you have this canceling that occurs. Now, I think if you go and you zoom in, like you might see that point of discontinuity. I'm not 100% sure on that, but in terms of where the vertical asymptote will be, though, that's the only one that will be present if you graph this out. So now let's look at some horizontal asymptotes and look at some of these situations. So horizontal asymptotes obviously are the ones that are flats instead of up and down. And in this case, this is done by a relatively simple rule. So what I'm going to show you here is, for example, if the denominator is a higher power than the numerator, then the horizontal asymptote is always going to be y equals 0. That is where the horizontal asymptote is always going to be. And if you need a way to think about this, the idea would be is that as x approaches infinity, the denominator is going to reach an infinite number faster than the numerator. All right, it's going to get there twice as fast. And so if you think about like these two functions racing against each other, this one's going to keep getting ever and ever and ever and ever bigger, and you're just going to see that line kind of drift that way. And that's how I sort of rationalize that with myself. X keeps getting bigger and bigger and bigger. Y is going to keep getting smaller and smaller and smaller as a result, until you get to a point where it equals 0. The only way that's ever going to change is if you have some plus k term here. So keep that in mind. But we're not really applying a lot of shifts in this case. We're just looking at a basic reciprocal function and going, well, what's going to happen in this case? And if there's no k value present, and you have a powered term that is higher in the denominator than it is in the numerator, it is always going to push the function to a place where y is equal to 0. Now, if we look at a different circumstance, so in this situation we have, both terms here at the first power, so they are the same. So if the numerator and denominator have the same power, then the asymptote is the ratio of y equals ax over bx, so to speak. And so what that means in this case, I guess I should just say a over b, because there is no x that's in that term. What that looks like in this case is that 3 is associated with the x, 4 is associated with the x. So the asymptote in this case is going to be y equals 3 over 4. And if you go and graph this out, again, you'll see this horizontal asymptote in that case. Now, the third example that I haven't talked about here is a situation where the numerator is a higher power than the denominator. And if that's the case, because the numerator is getting to a bigger number faster than the denominator, that actually forces a, this odd behavior, up and then down type behavior like we talked about in chapter 6 with the polynomials. And so what happens there is you actually don't have a horizontal asymptote at all that occurs in that situation. So if you see that where the numerator is a higher power than the denominator, then there is no horizontal asymptote. So now let's look at some basics of how to go and write out some of these functions here. So with this given situation, if we want to sketch this rational function, what we need to do is, obviously factor things out as best as we possibly can. So we can pull out an x, say x squared minus 4. We still have something that's x to the power, so we need to find a way to whittle that down. I notice it's a difference of squares. So we'll have x plus 2 and x minus 2 as our two options. And now we can go and write this new function here as 4x all over x times x minus 2 times x plus 2, and then we'll go and have these in place. Again, what this will allow us to do is that the vertical asymptotes will look like this, because if you can make the denominator equal 0, that's where the asymptotes are. So at x equals 2 and x equals negative 2, that's where those asymptotes are. With that in mind, you could have something weird happen at x equals 0, so be mindful of that. And then if you have a situation where the numerator is of higher power than the denominator, the denominator is higher power than the numerator, your horizontal asymptote, as we discussed in the previous slide, is y is equal to 0. So some important things to keep in mind. So if you're going to go and graph this out, all right, so you have this asymptote, and then at 1, 2, 1, 2, you have this boundary. Now this is a pretty normal function, and as x approaches negative infinity, you're going to see it approach 0, but it's going to be on the positive side because you'll have a negative over a negative, all right? And that's kind of how I think of it, as x approaches negative infinity. You know, how I think about this is that, hey, this is going to be a negative number over a negative number. So we're going to be on the positive side of the axis here. And so if we're going and drawing this out, that's going to help us to draw this. So that's one of the branches. And, you know, as, you know, let's say as y approaches, you know, let's say negative 2, well, you know, if you even plug negative 1 in here, you know, we'll say negative 1, that'll give us negative 1. So that's going to give us a positive number on the bottom, but a negative number on top. And so that's how it's going to start on this end. And I don't even need to really do much more, because what's going to happen is I have this asymptote here, this horizontal asymptote. So it can't go up to that point, and then it's going to go back down. You'll get this parabola underneath. And what you'll notice with these, you know, as you have a branch up here and approaches an asymptote, what always is going to happen at that asymptote is you're going to have a sign switch. So really most of the trick is probably just figuring out where that first branch is, understanding you're going to see that switch, following the asymptotes, and then you're going to notice this switch again. And then you'll notice this other branch here. And now we just drew this. And if you want to go and graph this and check this out, it's kind of cool that you can anticipate some of this behavior in such a simple manner, such as this. So something definitely kind of cool. And I want you to be able to anticipate this behavior a little bit, because I think that's valuable. I think that being able to understand some of that mathematical relationship around you can be really useful for you to take advantage of. And so in this next situation, what I'm going to do is I noticed that the higher power, or the numerator, is a higher power than the lower power. So I already know that there's no horizontal asymptote. And the other thing is those cancel out. Y is equal x. And so there is no vertical asymptote as well. It's just y equals x. And again, if you whittle that down and you break everything down to their simplest binomial forms like this, you notice with this one that this is just a horizontal line of y equals x, and you can again confirm that if you sketch it. So just some interesting things to keep in mind as you're going through this and how to analyze some of these, and hopefully this just adds a few more tools in your satchel or toolbox or bag, backpack, and gives you some additional ways to look at some of these more complex reciprocal functions that have, you know, a numerator function and a denominator function that we're looking at. So with that said, let's do some math.